This lesson is in collaboration with Flip Academy, which is a free online platform for all of your GCSE, A-Level, IB and CBSE needs. It's out now at www.flip.academy, and it's also available as an app for iOS and Android. It really is better than the other GCSE platforms out there. It has all of these lessons online. It has more topics and practice questions for you to go through. Hello and welcome back to Flip Academy. Today we're going to be looking at the first part of the complex numbers section of your spec. So this is specifically the stuff that turns up in paper 3. So to start with, we're just the basics, the pure basics, is understanding the idea that a complex number and what it is. So what it is it's a number that has a real component, a real number, plus an imaginary number. So what does this exactly mean? Well, a real number is pretty much every number you would have come across up until GCSE. So anywhere from negative infinity to plus infinity, any decimals, fractions, irrational numbers, anything is a real number. Now an imaginary number, there's actually only one, and it's simply the square root of -1, which is I. So it's basically just however many I we have, so 5i, 6i, 7i, etc. So a complex number has both of these parts. So as an example, you can have that, for example, you could have 3 plus 4i. And of course the real component is the 3, and the imaginary component is the 4i, okay? Where I is the square root of -1. Okay? So the notation that you would have is z, generally speaking, represents a complex number. R-E-Z, so if you have R-E of Z, it's just the real part of the number, so real part. So in our kind of example back there, Z was equal to 3 plus 4i. So R-E-Z, so the real part of it, would simply be 3. And then to work out the imaginary part, or to denote the imaginary part, we'd say I-M of Z. That's the imaginary part, which in this case is just equal to 4. It's not equal to 4i, it's just 4, okay? So we're just looking at the actual numbers themselves. Okay, so that's hopefully not too bad. So we've done the first two, so the meaning of the real part is just the kind of real number. The imaginary part is whatever's next to the I. Now we're going to work out, or I'm going to show you how to work out the modulus, argument, and conjugate, and use the fact that two complex numbers are equal if and only if both real and imaginary parts are equal. So for instance, if I took this being Z1 and Z2 being something like 4 plus 4i, those two numbers are not equal. They're only equal if all of the parts are exactly the same. So we've done that last bit, so now it's how to work out these three things. So first of all, we're going to start with the modulus. Now, I'm going to introduce a term that you may not have seen before, but the modulus is basically the distance from the origin on an Argand diagram. Okay. And you may think, okay, that sounds a bit weird. Essentially, Argand diagrams are ways that we can represent complex numbers, and they're actually quite simple. So you have kind of axes just like normal, but instead of x and y, we instead have RE for real and IM for imaginary, and that's literally it. So with our example here, where we had 3 plus 4i, it would be 3 across on the real axis and 4 on the imaginary axis, so we can say that that's 4, that's 3, draw a nice line, and then all it is it's the distance from the origin. So you may already know how to work this out. It's just Pythagoras, right? All you need to do is do this squared plus this squared and square rooted. So in general, you would have like an x and a y value, or whatever. So the modulus is equal to that. So again, it looks at the notations is the same with a vector. You'd put these two parallel lines to denote that it's the modulus, and all you do is you take the square root of the imaginary part squared plus the real part, and then the imaginary part squared. Okay, so it's not too bad. It's exactly the same as vectors, realistically speaking. So again, if we have the 3 plus 4i like we do here, in our expression, it's going to be 3 squared plus 4 squared, because again, we're ignoring the I. which gives me 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. And remember, modulus can only be positive, okay? Because it's a distance. Distance is always positive, right? I wouldn't say the distance from London to Manchester is negative 20 miles or something like that. What about with the argument? Now, the argument is where it gets a bit trickier. It's a bit more unique, okay? And it is just for complex numbers. So the argument is the anti-clockwise angle in radians that it makes starting from the real axes. Starting from the real axes. So in our expression here, or in our kind of diagram here, it'll be that angle, like that. And the notation for this is, honestly, it's actually not too bad. It's just arg of your number. So a bit uncreative, but it's not too bad. Normally, the argument is going to be between pi, arg z, and so negative pi and pi. And what a negative argument means, so if you think about it, that does kind of make sense, right? Like, if we look here, it's either going to be pi radians this way or it's going to be pi radians that way. So we normally denote those as negative pi if we're going clockwise and normal pi if we're going anti-clockwise. If you remember using the cast diagram when we were doing a kind of solving trig equations, it's essentially the same thing, where we go anti-clockwise for positive and clockwise for negative. That's why it's normally between minus pi and pi. Okay, because if I said, for example, minus 2 over 3 pi like over here, that's the same as just having a quarter pi, or pi over 2 this way. So, a negative argument, negative means below x-axis. And again, it's literally the exact same way we do it with the cast diagram. So, all you need to do is use the right angle trig. Exactly like doing the cast diagram. So, for example, if we have two questions, let's find argument of. So, find arg of. And I'll give you two examples. So, the first one is going to be z equals 2 plus 3i. And the second example will be z, or w, let's use a different letter, equals minus 1 minus root 3i. Okay, so we do two different examples because we're going to get a positive and a negative. I figured it might be smart to give you both. So what we're going to do is first draw the Argand diagram. So I know this is going to be in the top right quadrant, so I'm only going to draw the top right quadrant. We have RE here and we have IM here. And I'm going to draw the line, and it's going to be 2 on the real axis, 3 on the imaginary axis, and we're trying to work out theta here, theta. So to do that, we have the opposite side, which is going to be 3, and we have the adjacent side, so we're going to be using tan. So we have here tan theta equals opposite over adjacent, so 3 over 2. So theta is just equal to the inverse tan of 3 over 2. Again, make sure your calculator is in radians mode, just in case. And you should get an answer of 0.983 rads. Okay. Perfect. And for the next part, we have minus 1 minus 3i, minus root 3i. So I know this is going to be in the bottom left quadrant, so I'm going to draw out thing here. It's going to be down here somewhere. This is going to be 1, this is going to be minus square root of 3, and what we're going to do first is we're actually going to work out this angle, but the angle we're looking for is this, so we can call that phi, for instance. Okay, so what we can do is if we find this angle here and we just make it negative, just like the cast diagram. So yes, we are actually technically looking for this angle over here, which you can do. So you could just make it pi plus theta, or you can make it phi and make it negative. Okay, swap the sign. Either way is totally fine. I'm going to do it the kind of other way because, again, we normally give it in terms of negative pi to pi rather than giving a number bigger than pi. So I'm going to do it the other way. So if we do this, once again we have tan theta equals root 3 over 1, because again it's opposite over adjacent. So theta is equal to the inverse tan of root 3, which gives me an answer of pi over 3. That should actually be a value you vaguely remember. So doing 1 minus pi over 3 for phi gives me 2 pi over 3. So the argument, the arg of w, it should also be noted that sometimes, notation-wise, they don't put the w in a bracket, which I think is a bit confusing. So for me, I'm always going to put them in brackets, but just in case you see arg w without brackets, it just means the exact same thing. So the answer is minus 2 pi over 3. So again, you could technically do it as pi plus, but if you follow this notation, in most cases, we leave it as minus pi to pi instead because it makes a lot more sense. An agreed convention is good. The last kind of thing you need to be able to do is take the complex conjugate. Now this sounds difficult, but it's actually incredibly easy. Okay. The complex conjugate, we denote this by doing z star, right? Very pretty. All you do is change the sign of im. So if I remember our number from before, I think it's 3 plus 4i. The complex conjugate is literally just 3 minus 4i. Now this actually comes up a bit later because this actually gives us a different solution whenever we kind of want to solve something. And I'll explain what that means in a question a bit later on. But literally complex conjugate, all you do is you take the opposite sign. And you're going to be doing this a lot when you do things like division and also when you're solving equations too. So I think it might be fun for us to go through some facts, right? So if I change z to being any two generic, well, to being a generic complex number, then this is what I'd write. Yeah, that's what I'd write. So here's a couple of facts which would be fairly useful. Again, you can actually come to this naturally, right? But in a kind of your exam, speed is quite important. So I'm going to show you a few shortcuts which will hopefully help you out, and it will help you with any proofs that you may need to do and any questions that might come up. But again, you can prove these yourself, it's fine. So first of all, z plus z star is real. Always 100,000% of the time. Why? Well, if we have a look, we have a plus bi, right? I put it in brackets, plus a minus bi. So the two parts cancel out, and you actually just get 2 times the real component. That's it. So that can be useful to do, to know. The next thing is, so I'm actually going to put bullet points for these. Z minus Z star is imaginary. I'm just going to shorthand write that as IM. So again, let's look at that. A plus BI. And again, it might make sense the second I write this out. It's not exactly a complicated proof, but the A's cancel out in this case. And we have B minus minus B, which gives me 2BI. And lastly, and this is actually probably the most important one, and it's slightly more involved in terms of the proof. And this is actually a skill. But I'll wait until we finish this just to make sure we know what we're talking about. We have A plus BI, A minus BI. Now if we expand this, we get A squared plus ABI. I'm going to write it out fully, but you can probably see that the middle terms are actually going to cancel. And then lastly, we get minus BI squared. Now this is actually something that's going to come up again and again and again, I squared. And honestly, I make this mistake sometimes still. But I squared, because I is the square root of -1, I squared is equal to -1. So that would make this whole thing plus B. Okay? B squared. Right? So be really careful of that, because it's very easy when you're doing proofs to have a bunch of I squared terms and it flips the sign, but then it might flip it back because there's a minus in front. So if I had plus b squared I squared, it becomes minus b squared I squared. If I have minus b squared I squared, it becomes plus b squared. So it can be a bit tricky to remember to flip the sign. Okay, so be very careful about it. What I would do is what I just did here. I mean, obviously that's what I'll do. Is I literally work this bit out completely uniquely. So I cover up all of this other stuff and I'm like, okay, what is minus b squared I squared? I write the answer and then I write my next bit. And that helps me not make mistakes as often. Okay. Yeah, as you can see, that's real because there's only real components. So those are all the different things we need to be able to do. So complex conjugate, argument, modulus. It's not actually that much, but again, it might be brand new. In my opinion, modulus should be completely trivial for you because if you've done vectors. Argument, again, it's mainly cast diagram, but it can be a bit tricky. Complex conjugate, let's be real, not difficult. Change the sign of the imaginary part. That is literally it. So let's go on to some questions and see what happens. So we need to be able to add, subtract, multiply, and divide complex numbers. So this is actually really easy. When you add complex numbers, you literally just add the real and the imaginary parts. Same way you do with vectors, right? You add the I and j components together. So if I were adding two things, just like we did here, I add the real numbers and I add the imaginary numbers, right? It's just algebra, right? Just algebra. Subtraction, exact same method here. See, I didn't do anything differently. And multiplication, again, I didn't do anything differently. So adding, subtracting, and timesing are all the complete same. It's just algebra. So if you're reading this and you think, okay, adding and subtracting and multiplying complex numbers, oh, that sounds crazy. Just remember, it's literally just normal algebra, right? You have like terms. You have an I term and a normal term. Collect them. That's it for adding and subtracting. Timesing, again, you're just timesing out brackets. It's basic algebra. With dividing, things get a little more interesting because we always have to write them in the form x plus iy. And we have to do something that's very similar, but not exactly the same, but similar to rationalizing the denominator. So if I write u over v out, u is 1 plus 3i, so we have 1 plus 3i here, over 4 plus 2i. Now the problem with this is we can't just divide normally. What we need to do, and the reason why we can't divide normally is because we have an imaginary component. So we need to get rid of the imaginary component. So we do the exact same thing as with rationalizing the denominator. You times the top and bottom, and you just flip the sign. Now, I've done that intuitively. I need to get rid of the imaginary part, so I'm going to times it by the opposite sign. If you notice, this is just the complex conjugate. So in general, if you want to divide two numbers, complex numbers, you do u over v times top and bottom by the complex conjugate of those numbers, right? The reason why I wanted to show you this way first is to show you that it is just it's intuitive, okay? And if you didn't manage to work that out, that's completely fine, but it is somewhat intuitive. It's just like rationalizing the denominator. You can't divide when you have square roots in your denominator, so you get rid of the square roots. You can't divide when there's imaginary numbers in your denominator, so you get rid of the imaginary numbers, right? Not too bad. And all you do is times it by the complex conjugate. I wouldn't personally bother remembering this, but this is the technical definition. Instead, I'll just remember the logic behind it. But let's keep going. I'm going to write this out in quite a few separate steps because it's very easy to make mistakes. So, or should we, if I put it in brackets here, we're going to take the steps very carefully. So 1 times 4 gives me 4. 1 times minus 2i. 3i times 4 is 12i. And again, now you're basically just treating I as algebra. And then you have minus 6i squared, with the exception of this 6i squared bit. And this is divided by, well, we should know already from our previous expression, you're just going to get a plus b squared. But we'll do it properly. 16 minus 8i plus 8i minus 4i squared. Okay, so if we look at these separately, I squared is minus 1 times minus 4, so that would be plus 4. This would be plus 6. So now we can simplify. We have 4 plus 6 on the top, so that would be 10. Minus 2 plus 12 is also 10i. Over 16 plus 4 is 20. And that's it, actually, it's just 20, so I'll put that more in the middle. And now all you do is you do the normal division. So 10 divided by 20 would be a half. You can leave it as a decimal if you like, but decimals are disgusting. Plus a half I. And that will be your answer. 3 marks. Basically, it's just a rationalising the denominator question from GCSE. So it's not really too bad. Hopefully that makes sense. However, I'm going to also do this one just to make sure that you're completely okay with it. It's a bit longer, so this is without using a calculator because some A-level calculators can actually do complex numbers, but that's very naughty. Don't do the complex conjugate straight away. Just like, again, with rationalising the denominator, you would expand these brackets first, so expand the brackets first. 22 plus 4i. I can do, if I am allowed to do this one a bit quicker, so 2 squared is 4. Then you have minus 2i minus 2i, so minus 4i. And then you would have minus I squared. Right? Yeah, perfect. Well, no, plus I squared. See, almost got me. And that is equal to minus 1. So we get 22 plus 4i over 3 minus 4i. Okay. Perfection. So, now we need to do the division, so we're timesing the top and bottom by the complex conjugate. Basically just change the middle sign. That will give me 22 times 3 is 66, 22 times 4i, so plus 48, 40, 88i, God, plus 12i, and plus 16i squared over 9 plus 12i minus 12i minus 4i squared. So again, this will become minus 16, this will become plus 4, so let's write that out. We get 66 minus 16, which is going to be 50. 88 plus 12 is 100 over, so it becomes plus 4, so 9 plus 4 is 13. That should be 16. That should be 16, that's my bad. See, I told you, it's easy to make mistakes. Plus 16, so 9 plus 16 is 25. And then if you were to do the division, you'd get 2 plus 4i, which is a very satisfying answer, and it's also the answer to the question. Perfect. So hopefully that wasn't too bad. Again, it's easy to make mistakes, so take it kind of carefully. That's why I was constantly rereading the work to kind of avoid any mistakes that I was going to make, which is how I spotted this much faster than I normally would. And yeah, this looks a bit strange, but z is equal to 50 over 3 plus 4i. Finding the form a plus ib, z and z squared. So yeah, finding the form a plus ib. So basically, it just wants us to rationalise the denominator for part A. Right, so you might just think, oh, I can just rewrite the same thing, but look, a plus ib. So we're actually going to be rationalising the denominator. Again, it's not technically called that, but we're going to be doing the division itself. And to do that, we get rid of the complex, well, the imaginary part of the denominator. So work it out, we get 150 minus 200i over 3 times 3 is 9, and then we'd have the cross terms, but I'm not going to bother doing it, minus 4 times 4 is 16i squared, so that's actually plus 16, right? So it's 150 minus 200, minus 16i squared would be plus 16, so it's over 25 again. And that equals, that should have an I on the end. So 25, so it's 4, 5, 6 minus 8i. Yep, which is perfect. And lastly, we need to do z squared. So that's just going to be a classic, I say classic, just a multiplication. So we have 6 minus 8i. Again, I wouldn't recommend doing the original expression because that gets a lot more tricky. We're just going to use the expression that they give us. 6 times 6 is 36. and then it would be minus 48i minus 48i, and then plus 64i squared, so that's now going to become minus 64. 36 minus 64 is minus 28, and then minus 96i, and that would be your answer for that. Now for the last part, it says use the result that for a polynomial equation with real coefficients, any non-real roots occur in conjugate pairs. So when you have like polynomials like this, where you have a cubic or you have a quartic or something like that, generally speaking, you're going to get real and imaginary numbers. So do you remember when you were doing the quadratic formula back in the old days, and you would get math error sometimes, specifically when b squared minus 4ac was less than 0, and we'd say, oh, there's no solutions. We'd actually say there's no real solutions. Now you know why we said no real solutions, because we are now going to actually include any of these negative values by actually having imaginary or complicated solutions, okay? So, quite simply, if they give you that there is a solution here, which is a complex number, the other one is always just going to be the complex conjugate. That's it. The interesting thing about this is that they always occur in pairs. So if you have one solution, there is always another solution, which is the complex conjugate. And that is it for part 1 of complex numbers. We've already done this, representing numbers geometrically by means of an Argand diagram. So that is the last thing we need for part 1, but there is a part 2 for complex numbers where things get a lot more spicy. But we're going to handle that in the next video. For now, try and consolidate what you know, and I'll definitely see you in the next one.